Welcome back to P4. Today we're looking at equation of a straight line in 3 dimensions. Now, this is probably the hardest thing to get your head around initially. Some of you will struggle with this initially, but I promise with a bit of work and a bit of practice, it will become clear. So, imagine we have a straight line that is passing through a point that we know. And it's going to go towards some point R, which is along here somewhere, okay? And the line that passes through A is going to be parallel to vector B. So that's my start. So we've got a point A that we know. We've got a vector passing through it that is parallel to B. So initially what we can say is that the vector A to R is some multiple of B. Okay, hopefully that makes sense so far. Now the next thing we want to look at is position vectors. Okay, so what we actually want to do is we want to find the position vector of R. And to do that, we need to think about the origin. So let's start by joining A up with the origin. So now I've joined both A and R to the origin, then the position vector of point A is going to be vector little a, and the position vector of point R is going to be little r. And what I'm trying to look at here is essentially the position vector of R. So if I think OR is going to be O to A plus A to R. And OR is small r. That's that position vector one. OA is A, and AR is lambda B, some multiple of B. And here we have the first idea of an equation of a line in 3 dimensions. So R is the position vector of the point capital R, which is somewhere along that line which goes through A and is parallel to B. So this is my first one. I'll write it down here. R equals A plus lambda B, where lambda is a scalar parameter. So it's just a constant, if you will. It's just a number, but it gives me that multiple of B just for its size. Now sometimes this vector B here is known as the direction or directional vector, because if you think about it, I want to find out what this position vector of R is to this random point along my line, and I go from the origin to A, and then I go in the direction of B, okay, which is why this is known as the direction vector. And this will be, the position vector of A, so it's the same as the point on that line. So you're thinking about it in relative to the origin, we're finding the point along that line, and then we're going in a direction for this amount of size, magnitude. Okay, and that is what's going to give me the position vector of R. So we looked at what happens when we have one known point and the direction. Let's have a look at if we have 2 known points. So this time I have a line that is going through 2 known points. So that means that this line is also essentially parallel to this vector. Okay, so we don't need the direction like we did in the last one. The direction is the vector that is between these 2 points. That's the directional vector. Now, comparing with the origin, so we can think of the position vectors. We have a position vector C and a position vector D. just so, as a way, we're using C and D as we used A and B in the previous one. So this vector that goes from C to D is going to be the vector D minus C. So I'll put it up here. So C to D is C to O plus O to D. So minus C plus D, or D minus C. Okay, so that's my direction there. Now, same as the last one now, imagine that I put a point on this line and we'll call it R. Now, this is, like before, going to be the position vector R. And very much in the same way as previously. So if I want to find this vector OR, which is my position vector R, I need to go, say, C, and then a multiple of this CD here. Okay, so if I think about, CR is going to be some multiple of CD. Okay, so OR is going to be O to C plus a multiple of C to D. And O to C is C plus a multiple of C to D, which is D minus C. And of course, OR is R. So that gives me this as my second type of equation. So a vector equation, and again here, this is the direction. Now, before I go any further, I used mu in mine, but what I'm going to do is I'm just going to change that to a lambda, just to stay in using the same unknowns, the same parameters as your textbook, just so it makes a little bit more sense. So hopefully there we are, that makes sense. Now, you notice when I was doing this OR, I went OC and then C to R, which is a multiple of this CD. Well, I can obviously go, instead of O to C, I could go O to D and then a multiple along here. So an alternative could be that R equals D plus a different multiple of DC. Okay? Because I could go up D and then along, but this value here, the length of this is going to be different to the length of this. So DR is different size to CR. So I'm using that, I'll use that mu in this one. So this is a vector equation of a straight line passing through the points C and D with position vectors C and D. Okay, and lambda is a scalar parameter again. Just recapping, we're finding that position vector of R, and we've got a line that goes through 2 points that we know, C and D, and R is somewhere along that line. Okay, so you want to find that position vector, and that's where the equation comes from. So R equals either of these two versions. So straightforward example here, we have a straight line passing through the point A with position vector 4, minus 3, 2, and is parallel to this vector. So we can see that A is 4, minus 3, 2, and B is 5, 0, minus 3. So our equation, which is R equals, is going to be the A plus lambda B. An alternative way of writing this would be R equals 4i minus 3j plus 2k plus lambda times 5i minus 3k. Again, another way is I could expand them and put the i's together. So 4 plus 5 lambda I minus 3j plus, we get 2 minus 3 lambda k. And then finally, I could put it all together in a column vector. So this would be 4 plus 5 lambda minus 3, and then 2 minus 3 lambda as a column vector. So you've got a few options of how to phrase this or how to write it. Okay, in the form of column vectors, in the form of I and j. So you've got two options for the column vector and two options for I and j. What I would say is that if I was going to be doing any kind of calculations with this, I'd be using it in terms of a column vector. So like this bottom one here would be my preferred method if I'm going to be using this in a later part of the question. Second example here, now we're going to have 2 points, A and B. So the position vector of A is the same as the coordinates of A, and the same goes for B. Now we need the direction, so that is going to be B minus A. So 5, 3, 4 minus 3, 1, 6. So 5 minus 3 is 2, 3 minus 1 is 2, 4 minus 6 is minus 2. So my vector here would be 3, 1, 6 plus lambda 2, 2 minus 2. Now I've got lots of options for this one. You know, I could also use B as my starting point. Obviously this value of lambda would be different, so actually maybe instead of lambda let's use mu. Okay, and again, same as before, I can write it in terms of I and j, or I could write it in terms of a column vector. So I'll pop those down now. And of course I could do the same for this one. Now it's also worth noting that while I've done a B minus A, assuming the way it went, technically we could also do it the opposite direction. Our value of lambda or mu would be the opposite sign. So it is possible to do it another way as well. Now, if you're unsure, just stay tuned. So, like this first one, 3i, so the coordinate 3i in the x direction, and then the line is going to go in the y direction. Okay, this one, we've got lambda times I plus j, so that means it's going to be like 1 across, 1 up, 1 across, 1 up. So it's this, it's like the line y equals x. Looking at this one, starting coordinate minus 4, 2, which is why I went across and up. And then the direction is 2 to the right, 1 down, 2 to the right, 1 down. So it's that direction there.